In computer vision and robotics, linear algebra plays a very big role. So computer vision and robotics, they use linear algebra to translate physical word geometry into digital coordinates. So if I talk about computer vision in particular, so in computer vision, digital images are stored as matrices of pixel values. So in computer vision, we represent digital images as matrices of pixel values. Operations like the edge detection, blurring, or rotating are performed by applying linear transformations, that is a matrix multiplication, to these pixels. So the operations on the image is basically the linear transformations of these matrices. So the idea is that in computer vision, we represent digital images as matrices, like we represent it as a pixel matrix, a matrix containing the pixels. And the operations on these images, like the edge detection, blurring, and rotating, is basically the linear transformations on these pixel matrices. So, hence, computer vision heavily makes use of linear algebra because whenever we are talking about matrices, we are talking about linear transformations, we are talking about linear algebra. So, linear algebra is used to represent digital images and also to process digital images. Similarly, in robotics, if we talk about robotics, in robotics, engineers they use homogeneous transformation matrices to model a robot's pose, that is a position and orientation. So the modeling of a pose of a robot is done using homogeneous transformation matrices, which is a concept of linear algebra. Even like solving inverse kinematics, like calculating how joints must move to reach a specific point, is a complex system of linear equations. So in inverse kinematics also, it involves complex systems of linear equations, which is a part of linear algebra. So now it's very clear that if we talk about linear algebra, it has applications in computer vision and robotics. In computer vision, we represent digital images in the form of matrices, pixel matrices, and processing of image is basically the linear transformations performed on the pixel matrices. Similarly, in robotics, we use homogeneous transformation matrices to model a robot's pose. And to solve inverse kinematics, we make use of complex systems of linear equations, which is a part of linear algebra.